Good afternoon and welcome to Track 5 Industrial Coatings at CTT Virtual Week. I'm your moderator, Kristen Johansson, Editor-in-Chief at PCI Magazine. Thanks for joining us. This presentation is titled A Novel Reactive UV Absorbing Diol. Our presenter is Dr. George Maurer, Research Scientist at Chitec Technology Corporation. George focuses mostly on the use of UVA, HALs, and AOs in the stabilization of organic materials. He has 36 years experience at PPG in a variety of solvent-based, water-based, powder coatings, and resin technologies. George contributed to all automotive coating layer technologies and culminated his OEM tenure as the Global Director of Sprayable Technologies. He holds 12 U.S. patents. Don't forget to submit your questions, and later in the program, we will address as many of them as time allows. And now, George, I'm excited to turn it over to you.
Thanks, Kristen, and thank you all for joining. Today, I will describe for you a new UVA. It's dihydroxy functional. We'll call it Diol R455, and it is designed to be easily reacted into polymer systems, such as coatings or other polymeric materials. The big advantage of this reactable feature is that the UVA is no longer susceptible to loss through migration. Okay, for any discussion on light stabilization strategy, I like to start off with some background science. So here goes. The general strategy for obtaining good exterior durability in coatings is to use oxidation-resistant polymers and to use absorbers to absorb harmful UV light and then capture any free radicals that form using hinterdimming light stabilizers. The UVA's effectiveness follows Beer's law, which is shown here on this slide. And the factors that impact Beer's law are which UVA is used, recognizing its coefficient of absorptivity, epsilon, and then the UVA loading in the formula and the thickness of the film. These all determine how much light gets absorbed. And one factor that is often neglected is the loss of UVA over time. Various migration loss pathways are common and sometimes even problematic. In this presentation, we will show that using reactable UVA, like this new Diol R455, eliminates this problem by tying the UVA down in the film through covalent bonds. And in this diagram, we're trying to illustrate how migration promotes the loss of UVA from films. You'll see in subsequent slides how Chitec experiments show that Diol R455, when reacted into films, does not lend itself to extraction. We also will show evidence of unbound UVAs being lost from films. Field experience bears this out, with some UVAs being completely lost over extended outdoor exposure. We are just beginning to show how some of the various extraction materials present in the environment go to work on our films. Some materials that promote migration are fuels, water, windshield wiper fluid, brake fluid. Those are all automotive, more or less. But for airplanes, there's Skydrol, also car wash soaps, degreasers, cleaning fluids like alcohols, mineral spirits, solvents. I could go on and on. There's all kinds of materials out in the environment that can aggravate the migration and extraction of UVAs from coatings. So all these materials may be responsible for those odd field failures that we often see. Okay, in this graph, we're showing how the UVA concentration decreases with time and exposure. Standard testing does show migration loss or degradation loss, both. What it doesn't show is what is possible when aggravating exposure conditions exist, like strong car wash soaps and so on. These dotted lines that I just added are meant to represent the extra loss due to various migration possibilities. And of course, where that dotted line goes will vary by what the environment is and what the coating is exposed to. So in general, the triazine 5400 outlasts the benzotriazole family of UVAs, and you can see that in the diagram. And benzophenones are most fugitive and really aren't used for applications where you need very long-term, high-performance type durability. Yeah, first I want to show in normal UV activity, we have this cycle between excited state and ground state, and it should go back and forth. But if you've got the migration, then you get loss through oxidation up here. Materials on the surface can get exposed to more free radicals, dirt, rain, pollen, and so forth, and then they degrade or are lost quicker. And of course, sublimation is a big problem as well. So loss rates for the smaller UVAs can even be exceedingly high. So we really need to figure out how to minimize the migration. And so here's the structure of the diol. And you can see down here two primary hydroxyls. And they react with a variety of common functional groups, like the isocyanates and melamines, siloxanes. The strategy here is to tie down the R455 during cure of an enamel, or the R555 can be pre-reacted into a resin during polymer synthesis. So either strategy works well. The benzotriazole ring has the usual excellent adsorptivity, covering the whole terrestrial range of the UV spectrum from 290 to 380 nanometers. Okay, this polymer block diagram shown here represents what an R5 polymer structure might look like. In this case, we're showing R455 in combination with a polyol and a diisocyanate. Chemists can obviously use their own strategies with hard or soft components and to vary the functionality of the isocyanates or the hydroxyls. Obvious alternatives are to use triols or triisocyanates and so forth. To use diol R455, you just need to look at the R455 as another polymer diol in your resin or paint formula design. It's really pretty straightforward in that regard. Okay, the material is usually a very light color, like a benzotriazole always is. It doesn't bring in enough color to impact a coating at the usual coating thicknesses. So if you go 25 to 50 microns, things like that, you can't really see the yellow color. Its solubility allows for a very practical synthesis and formulation, and it's delivered a very high degree of purity. Our assay is listed at 98% or better. So that's pretty good. Okay. Here's the UVA loss over time graph again. Here we're showing a straight line across the chart for accelerated testing, but it also, whoops, here, let me give you one more. There we go. Just put in the diol R455. And you can see how it starts off very much like the triazine, but it's expected to stay up there, and I did not draw in a dotted line to represent how much is lost during migration or extraction in the environment. And the other ones go down. Some go down. There's some benzotriazoles that in Florida after 2 years go down to actually zero. Benzophenones 2 years in Florida are trashed. Triazines often last pretty well. And of course, we're trying to target a new gold standard for migration-resistant durability, having it stay forever or for a very long time. Okay. In this automotive refinish 2K clear coat case, we saw the R455 perform equal to the triazine 5400, which is a premium UV absorber, and the R455 outperforms commonly used benzotriazole. In this case, it was 5530. In environments where migration loss aggravators are present, we expect the R455 to perform even better. Okay, in the next few slides, we'll show some data supporting our migration resistance performance claims. And now on this slide, we are comparing R455 to a non-reactable benzotriazole, 5582. the R455 is expected to react with a melamine crosslinker. In this case, it's Cymel 325. And for the experiment, we chose methylene chloride as the UVA extraction solvent because it's a very aggressive solvent. It really swells the coating, and it should extract most things that are not cured into the film. And just to note, the purpose is not to simulate a common outdoor vent. We know that methylene chloride does not exist in a car wash or anything like that. But really what we're focusing on here is just proving that the R455 is bound to the polymer network. And we put a control in really to show that our test method is capable of extracting free UVA. Okay, now here's the results of the extraction experiments. We did quantitative analysis and by HPLC, and you can see we got almost quantitative extraction. 99% of the benzotriazole 5582 was removed with a methylene chloride extraction of the cured film. And we got, essentially, it was very difficult to detect. It was less than 5% of the Diol R455 was extracted. So our theory really works. We are tying down our benzotriazole into the film, and it does not migrate. Okay. In this next test, we are using a much less aggressive method to extract the film. It's a water-ethanol mix. Might not be too different than windshield washer fluid, something like that. And this should give us a better feel for whether or not mild aggravators can extract the UVA. In this case, we drip the solvent onto the surface, wash down the panel, and for a control, we chose our best non-reactable UVA, the 5400 triazine, for comparison purposes. Okay. And then the extracts were analyzed by UV spectroscopy, and they clearly show that much more 5400 was extracted than R455. Essentially, no Diol R455 could be detected. The baseline was, we're getting down into the noise levels there using this ethanol water extract. So this reinforces our position that the R455 is tied down pretty well, and that the other UVAs can be extracted. Even a triazine can be extracted, which is a bigger molecule. Okay, in this next test, we're using 3M car wash shampoo to see if a simple water soap solution can impact migration loss of free UVA from cured films. We used a 2K polyurethane formulation for this test. The soap solution was pumped across the surface of the coating without agitation. You can see the setup is here. We are trying to simulate a realistic, longer-term, many car wash type situation. Okay. And again, we see the R455 is very extraction resistant, but some of the triazine 5400 was removed with a car wash solution. So we're continuing to reinforce our migration strategy here. Okay. Now, for this section, we're going to go over polyurethane dispersions, a little bit different type of application here in waterborne. And we're going to show how there could be some advantages in using a material like R455 in a waterborne dispersion. And really, this is because using solvent-borne UVAs in waterborne coatings is not always easy. You cannot normally formulate the solid UVAs into a waterborne coating due to solubility constraints. A UVA like CHIGUARD 5530 has a polyethylene oxide side chain, which does make it reasonable to formulate into a waterborne coating. But this UVA is somewhat less efficient due to lower active chromophore content, and it does not have long-term field retention due to worse photopermanence. So it's not a great way to go. There's also water-dispersed UVAs like the benzotriazole 5582 WB or triazine 5400 WB. These are better performing than the 5530 type. But they do not react into the polymer network, so they do still have the possibility of migration loss, just like we saw in solvent-borne coatings. Okay, so let's get on to an application. Here on this slide, we're showing a polyurethane dispersion where we just insert the R455 into the urethane as a diol monomer. The PC in this example is a polycarbonate diol, and the DMPA is dimethyl propionic acid, which is a diol that also provides a carboxylic acid for a later neutralization and this salt formation to give you good dispersibility in water. This is a normal strategy for waterborne. Stripping removes the acetone solvent, which was necessary to dissolve the DMPA during the polymer synthesis. So this is a fairly normal polyurethane dispersion synthesis strategy that we just looked at. And here's the result. The physical properties seem to be really quite normal. And this is just a plug-in. This isn't like, big reformulation. And we got particle sizes, which are very normal. So it really can be as simple as just substituting some of the diol R455 into a resin formulation in place of some of the normal diols that you use. Okay, and here we just are showing the molecular weight of this R455 diol inserted into the PUD at 8%, which is pretty high loading. And we see molecular weight right where it should be. So we're really very happy that it seems straightforward to incorporate the diol UVA into a PUD. Okay, in this experiment, we're looking at R455 in a waterborne 2K clear coat system. And we're testing it for color retention. It's over a dark blue base coat. And the diol R455 is pre-reacted into the waterborne PUD. So we are comparing this diol UVA PUD to 3 systems with different freely added non-reactable UVAs. And here are the results. And as you can see, the standard, the blank is terrible. And then the standard line is the green line with a free UVA, which is doing okay. And then the R455 is doing better. And then the triazine is also doing quite well. And this, keep in mind that in this experiment, we are not doing any extractions or other migration enhancing testing. So in the real world, if anything, we expect the R455 to perform even better than this particular graph shows. Okay. And in this example, we're just showing the robustness of use for this diol UVA. We're trying to define the limits of loading. And you can see at a 20% loading, which is extremely high, we start to pervert the PUD, and it would need reformulation in the resin portion to get it to behave well, which we're not saying you can't do. I think actually you probably can do it. But in just a plug-in replacement type situation, we're fine at 3 and 10%. So really, it should be easy to incorporate the R455 into a variety of different polymer formulations, something that a good synthesis chemist can do quite easily, we think. Okay. So in conclusion, we feel confident that the R455 diol does what we designed it to do. The diol reacts into the polymer system and thus provides a very viable approach to stopping migration loss of UVAs from coatings. And, our current status is we're commercial on 2 continents already. We have submitted registrations globally. Don't anticipate any problematic restrictions to use. TSCA has been verbally accepted. We expect our number this month. And we do have some handling requirements, normal respiratory protection, but I think for organic powders, people probably are already doing that everywhere. So we don't anticipate any big problems in that regard. In terms of opportunities and potential applications down the road, There's all kinds of different things that we think are possible. We talked a lot more about things like automotive and overlapped into industrial and maybe some aerospace applications, which are ones that we think are really good fits. But also in sealants and adhesives, windshield adhesives would be a really good idea. But also in potentially in contact areas like food and medical. If you need a UVA, this ties down so then it won't be extracted into neighboring materials. So we think there could be some big advantages there too. So a lot of neat opportunities for a Diol functional UV absorber. Okay, well, I'd like to thank everybody for listening, and we look forward to your questions and further discussions. Back to you, Kristen.
Thanks, George. That was a great presentation. We do have time for a few questions, so we'll get right to that. The first question is, do I still need HALs in formulations with the R455 UV absorber?
Okay, that's a good formulation question. The answer is yes. And in fact, there's some very good synergies of using R455 with a HALS. And whether it's a non-basic HALS like a 101 family or a basic HALS like a 353 or a reactive HALS like an 1152, they all can work quite well. And yes, absolutely, you need the HALS to go along with it. Okay.
Second question. Do both of the Diol UVAs react into the polymer?
Okay, that's a tough question, but a good one. Basically, if you have a good excess of isocyanate, if you're making a urethane, when I say good excess, 10, 20%, then we get most of them reacted in, so it goes in as a difunctional material. Of course, there'll be some that'll be one functional, and our experiments so far are really showing there's only a very small trace of unreacted where neither hydroxyl reacts. But if you have a situation where you're starved for the material that's reacting with hydroxyl, then of course you'll get less than two hydroxyls reacting. But if you get one to react, then it should tie it down. So I think we'll be in pretty good shape in a variety of formulation strategies.
Okay. Next question. What are the most common migration and degradation pathways, and are they well understood?
I think in a way they're understood in a general sense, but the real details of them get extremely complicated. And I think most people understand that in an outside environment, we have all kinds of different materials out there. Some pretty extreme. I mean, pollen and other plant fallouts. Bird poop is often really aggressive at even destroying good polymers. One of the things that's a lot more dynamic than people realize is just water. Water goes into most coatings, much more than people want to admit. It can swell the coating, and then that can lead to migration and degradation. And of course, you always have oxidation. Even with a good UVA, you can't stop getting some free radical formation. And that's why, related to the previous question, why the HALS is so important, that really shuts down that radical degradation progression, which is really inevitable. So really, there's a lot of different pathways. I think they're probably all important. Whenever we test a single pathway, we see that it is a factor. And the combination in an environment really depends on what that environment is. It's going to be different up north and down in Florida and so forth. So a lot of things happening. Our films are much more dynamic than we want to admit. Thank you.
Okay. Thank you, George. That's all the time we have for questions today. Please join me in thanking George Maurer and Chitec Technology Corporation for their participation at CTT this year. As a reminder, this presentation is being recorded and archived until August 2021 at PCIMag.com. We appreciate your time and hope this presentation has been helpful to you. Stay tuned for our next speaker.